Now continuing with the chemical kinetics, that is one factor I have already discussed with you, that is your catalyst. I have discussed with you the catalyst factor. Now I said you that catalyst, what it does, catalyst is a substance which alters the rate of the reaction. Without participating in the reaction, it alters the rate of the reaction. That means it provides an alternate path to carry out the particular reaction. Now I have to say a little bit more about it. Got it? About the catalyst, I have to say something more about it. Now, I have already said you that how the catalyst provides an alternate path. That is, it lowers the activation energy. As it lowers the activation energy, so for that particular purpose, what you find is that whenever you carry out the reactions with the catalyst, what you find is that is nothing but the reaction is faster. Same thing if it is a negative catalyst. Listen carefully here. If it is a negative catalyst, what it will do? Negative catalyst will retard the rate of the reaction. Positive catalyst accelerates the rate of the reaction, increases the rate of the reaction, but negative catalyst decreases, it retards the rate of the reaction. So remember that negative catalysts, which are known as inhibitors, which retards the rate of the reaction. Let me give you some examples of negative catalysts. Is that, like you have read it in class 11 that we are using tetraethyl lead. Alright, we are using tetraethyl lead, which acts as an anti-knocking substance. In petrol, we are adding a tetraethyl lead, which acts as an anti-knocking substance. What it does? It decreases the rate of reactions of, that is, the petrol, the combustion of the petrol, we can say that. Similarly, that is, we are using inhibitors. Got it? Inhibitors, like suppose for when the blood is not clotting, then we are using the inhibitors, which decreases the rate of the reaction. Similarly, the rate of transpiration, the transpiration which is taking place in the leaves. Alright, you find the dorsal surface of the leaf, it is nothing but it is being coated with wax, or naturally, it's not somebody's coating, naturally it's being coated with wax or some hairs is there. What is that? It acts as an inhibitor, it decreases the rate of the reaction. So they all act as a negative catalyst. When you are preparing oxygen from hydrogen peroxide, then the rate of reaction is very fast. Then you use inhibitors. Alright, it is so fast that you are unable to collect the oxygen gas. Alright, so for that purpose you have to decrease the rate of the reaction there. So in this way, many negative catalysts are there, many positive catalysts are also being there, which increases the rate of the reaction. Like when you are preparing oxygen from potassium chloride, manganese dioxide acts as a positive catalyst. KClO3 in presence of MnO2 will give you KCl plus O2. So manganese dioxide acts as a positive catalyst there in that particular case. Fine. So in this way, we are having two types of catalyst basically. One is positive catalyst, another is your negative catalyst. Positive catalyst increases the rate of the reaction. Why? Because it decreases the activation energy. But negative catalyst, what it does? It increases the activation energy. And as a result, it decreases the rate of the reaction. Because you know, activation energy is what? Is the excess energy which is required to carry out a particular reaction. That means to reach to which level? Threshold level. To reach to the threshold level. In threshold level, what is being formed? Activated complex is being formed. So if the activated complex is being formed at a higher energy level, activated complex is formed. Listen carefully. Activated complex, if it is being formed at a higher energy level, let us say this is the energy of the reactant. And if the activated complex is being formed at a higher energy level, then what you will find is that then the rate of reaction is decreasing. Alright, actually this is the what you can say, the graph for the actual rate. Now this much is your energy of the product. I can still come down. We can say that this is your energy of the product. We can say that is EP. We can say, and this is your ER. Clear? So in this way, what you find is that this is your activation energy. You can see. Now the blue line here, you can see this is with catalyst. This particular blue line with catalyst. So with catalyst means what catalyst it is? It is a negative catalyst. And the black line is without catalyst. Without catalyst. This one is without catalyst. I am not using the catalyst here. It is without catalyst. The black line is without catalyst here. I am not using the catalyst here. Got it? So when I am not using the catalyst, you see the activation energy here. It is up to this level. The activation energy is this. Alright, this is your activation energy when you are not using the catalyst. And when you are using the catalyst, you can see what happens is that the activation energy is still increased. So when activation energy is increased, the rate of reaction decreases. Alright, but the same thing, if you use, suppose this is the actual reaction, and now you rub this line, you blue line, you rub it. Alright, you rub this blue line and you make another blue line. We can say that another blue line. Let us make it here. This also I am rubbing it. Another blue line, I will make it here. That is, this is the graph you can see without the catalyst. This graph you can see. Now I am drawing a graph here. This is the blue line here. So this is now with the catalyst. So what catalyst is now? Positive catalyst. Why it is positive catalyst? Because you can see the activation energy here. The activation energy is lowered. So rate of reaction becomes faster. Now this is known as the activated complex or the transition state. So in case of what you can say positive catalyst, activated complex is being formed at a lower energy level. And in case of negative catalyst, you have seen it, the activated complex is being formed at higher energy level. Alright, so what we find is that as the higher energy level it is being formed, so hence the rate of reaction is slower, and it is being formed at lower energy level means the rate of reaction is being faster. Alright, in this way, catalyst, it does not participate in the reaction, just it increases or decreases the rate of the reaction depending upon the nature of the catalyst. Again I repeat, positive catalyst increases the rate of the reaction, negative catalyst decreases the rate of the reaction. Alright, now next is after that, if you see that is the characteristics of the catalyst, you will find that the catalysts are always required in traces, minute quantities, very small quantities. The catalysts are being required. Number one. Number two, at the end of the reaction, you get back the catalyst. How much catalyst you have taken it? You get it back, that much amount of catalyst, and it remains chemically unchanged also. We can prove it also. It remains chemically unchanged at the end of the reaction. How can we prove it? Let us say we have taken potassium chlorate as a schedule, KClO3, and I have taken MnO2 as a catalyst. It will give you KCl plus O2. So 2 KClO3 will give you 2 KCl plus 3 O2. Here manganese dioxide solid is a catalyst. If you won't use manganese dioxide, what will happen? The rate of reaction will be slower. By using manganese dioxide, rate of reaction becomes faster. So hence MnO2 acts as a positive catalyst. Now let us say I have taken MnO2 as a very small quantity. Let us say 1 gram. I can say less than 1 also possible. But less than 1 gram, it is difficult to weigh, isn't it? Practically. So in this way, let us say I have taken 1 gram of MnO2. I have taken it. Got it? Clear? Now this 1 gram of MnO2, what you see is that when the reaction is being completed, oxygen gas is evolved. You will see potassium chloride is a white residue, and a black also you can find a substance is remaining behind. What you do is that you take this particular black and white residue which you are getting it, you take it and you dissolve in water. KCl will dissolve in water, but not MnO2. You filter the solution. On filtration, you will get back 1 gram of MnO2 on the filter paper. How do you know it is 1 gram of MnO2 only, not any other substance? Do a test. You will do a test by which will be proved. Now MnO2, the 1 gram which you got it now, you can weigh it and find it out 1 gram, that you can see it. Alright, are you following what I am saying? You will get the black and white residue which you will be getting now. At the end of the reaction, you dissolve in water. KCl will dissolve in water, leaving behind a black substance. I have to prove this black substance as MnO2. I can weigh it and find it out it's 1 gram. That how much I have taken, I got it back. So that is what I am doing it. That black substance I will take and I will react with conc HCl. It will give you, what is that? MnCl2 plus water plus chlorine. I know it. How do I know that if chlorine gas is evolved? A greenish yellow gas will be evolved, you can see. When MnO2 react, the black substance react with HCl, conc HCl, a greenish yellow gas is evolved, proving that the given substance is chlorine. And here MnO2 acts as an oxidizing agent. So it is being proved by this reaction that the given substance is MnO2, because MnO2 only reacts with HCl to give you a greenish colored gas, that is chlorine. No other substance you can select. So in this way we can prove it also that the substance remains chemically unchanged at the end of the reaction. Now next is, what we find is that a catalyst does not alter the delta H of the reaction, the change in enthalpy of the reaction. Catalyst does not alter the free energy of the reaction, delta G of a particular reaction. Alright, it does not alter the delta G, it does not alter the delta H of a particular reaction. Change in enthalpy, neither the change in free energy. We can say that. A catalyst does not alter the equilibrium of the reaction. Yes, because when a catalytic reaction is taking place, it not only changes the, what you can say, the reaction, the rate of reaction in the forward direction, but also it changes the rate of the reaction in the backward direction. Listen carefully. in case of equilibrium reaction, in case of reversible reaction, a catalyst not only changes the rate of the forward direction but also it changes the rate of the backward direction. So ultimately the rate remains the same, due to which you find that it does not alter the equilibrium of the reaction. Alright, the equilibrium of the reaction remains the same because it not only alters the rate of the forward but also it alters the rate of the backward, due to which the reaction remains in equilibrium only. Alright, reaction remains in equilibrium. If you use a catalyst, what you will find that you will be getting the equilibrium at a faster rate. If you don't use a catalyst, you will be finding out that equilibrium will be attained but at a slower rate. That's the difference. Rate, the differences. Okay, so in this way you came to know what you can say about the catalyst. Now what I want to say one more thing to you is that catalysts are again two types: homogeneous catalyst and heterogeneous catalysts. Homogeneous and heterogeneous. Now what do you mean by homogeneous catalyst? Homogeneous catalyst means when the reactant, product and the catalyst are in the same phase, it is known as homogeneous catalysts. When the reactant, product and the catalyst are in the same phase, phase means either it will be solid or liquid or a gas, it is known as a homogeneous catalyst. If the reactant, product and the catalyst are in the different phase, okay, let us say the reactant is in the gaseous state and the catalyst is in the solid state, or the reactant is in the solid state and the catalyst is in the gaseous state. In this way, when the reactant, product and the catalyst are in different phases, they are known as, it is known as heterogeneous catalysts, and the reactant, product and the catalyst in the same phase, it is known as homogeneous catalysts. I am giving an example to you. It is a common example, you know that SO2 gas plus O2 gas. You know, you have read it in the lower classes. This reaction takes place in PT or vanadium pentoxide as a catalyst. You can say that. You can use it. V2O5 or PT as a catalyst. You can use it. To get it what? 2SO3 gas. 2SO2 gas will give you 2SO3 gas. Now this reaction also can be done. The same reaction also can be done by taking nitric oxide gas as a catalyst. Alright, nitric oxide gas as a catalyst. I can carry out the same reactions, we can say that. So it is a heterogeneous catalyst because here this is a solid. This is a solid, you can see. Whether it is PT or whether it is V2O5, it is a solid. And rest all are gaseous. Here all are gaseous. See this all are gaseous. Alright, so it's a homogeneous catalyst, this is a heterogeneous catalyst, we can say that. Next is a catalyst. What it does is that it forms an intermediate product, and the energy of the intermediate product, if it's a positive catalyst, it will be lowered. For that purpose, the rate of reaction becomes faster. Alright, it does not participate in the reaction. At the end of the reaction, remains. Alright, let me take this example only and explain you. Alright, now here I told you SO2 plus O2 in presence of NO gives SO3. Now first step, what happens is that NO, it's a catalyst. It reacts with one of the reactant, that is oxygen, to form NO2. Alright, this is your intermediate product. 2NO plus O2 gives 2NO2, we can say that. Clear? Now NO2 reacts with another reactant, that is SO2. Another reactant. See, I am writing here R1, R2, and this is your intermediate product. To form, what is that? It is nothing but NO plus SO3. This is your product and this is your catalyst. See here, NO2, here see, N1, oxygen 4, 3 plus 1, 4, sulfur 1, see. So what you got it back? You have taken nitric oxide as a catalyst. You got back nitric oxide. So what it does? Catalyst, it lowers the activation energy. The first step you can see, catalyst, what it does? It forms an intermediate product, and the intermediate product is formed at a less energy, lower energy rate it is being formed, due to which the reaction becomes faster. So in the second step, what happens is that it reacts with SO2 and we get the product. In this way, the catalytic reactions is being carried out, so to say. Clear? This particular theory which I have said here, it is known as intermediate compound formation theory. This theory is known as, because this is an intermediate product, an intermediate compound. So this theory is known as intermediate compound formation or intermediate complex formation theory. Thank you.